Hello and welcome. Electricity and Magnetism, Part 7. Today I'm going to talk about current, resistance, and electromotive force, or EMF. So we're going to start with current. So far we've seen electric field, electric potential, capacitors, and these all had to do with static charges, like electrostatic force between 2-point charges, etc. What if these charges are moving? Okay, let's talk about that. Moving charges. And I'm talking about a group of charges, okay? Many of these charges, like inside a metal, inside a conductor. Moving charges inside a conductor, a conducting material. Now, most common case is maybe a metal, a copper wire, but it's not limited to that. It could be a gas, ionized gas, where you have charges, plasma. So we have positive charges and negative charges. So these are possibilities. Okay, we have charge-carrying particles. In the case of a metal, this would be the free electrons in that metal. So normally meaning you don't do anything to the metal, you don't apply any electric field or anything, you have already electrons which are free, okay? The protons, the nucleus of the metal, is of course fixed at fixed locations, but these guys, these atoms share their electrons. So the electrons will move from one to another. Okay. So these are called ions, by the way. Ions, which are positively charged ions. If you lose electrons, for instance, if an atom loses an electron, it becomes a positively charged ion. So these don't move. What moves is the electrons within the conductor. So that's when there's no electric field. You don't need electric field or an external electric field, let's say, so that these electrons move even when there is no electric field, no external field. Those electrons will move from one place to another, colliding with these ions and changing directions. It's a pretty much random motion. So an electron would be moving like this. And these are happening too fast, okay? On the average, there's no really displacement, all right? But they're moving really fast. I mean, it's in the order of 10 to the 6 meters per second. But they don't go all the way from one end to the other end. They collide with ions and change directions, like scattering, you know, like billiard balls scattering by other billiard balls. But what happens when you apply an electric field? All right, so this is your conductor. Let's say at t equals 0, this is the starting point of your electron. It went like this, like that, this way, came back like this, and like that, okay? Made 1, 2, 3, 4, 5, 6 moves. If you apply an external field, let me show it with blue. Let's say the electric field is to the left. This is your electric field inside the metal. All right. What happens is while the electron moves, it's going to experience a force, right? There's going to be a force experienced by the electron according to our relation here. So if E is not 0 anymore, then you would expect this electric field to affect the motion. So basically, this happens in delta t time, right? In delta t, instead of starting here and ending up there, because of the force, remember, if the electric field is to the left, the electron will experience a force to the right. So that probably it's going to move something like this. I'm exaggerating, assuming that the collision points are same. So it's going to be still going under those collisions, but while on the move, it's going to move to the right a little bit by the influence of that force. So instead of ending up here, this point here, instead of this point, it's going to end up after delta t seconds right there. Okay, so this kind of motion happens in delta t, right? So the distance traveled then in that delta t time interval, instead of ending up here, it ends up here. So this distance, this small change, is delta x, okay? This happens in delta t. So you could apply a basic kinematics logic to it, and what if delta x is equal to some velocity, which we're going to call drift velocity, times this delta t. All right. So remember, the velocity of the electrons between the collisions was in the order of 10 to the 6, very fast, okay? But this drift velocity is relatively small. I mean, orders of magnitude smaller. So VD would be about 10 to the negative 4 meters per second. All right. So this kind of motion I'm talking about, all right? This is the kind of motion we have for electrons inside a conducting material when there is an external electric field present, all right? So this kind of motion will be similar to the other motion of other electrons, and you have billions of these. So what happens is a net movement of electrons from left to the right for this specific case, okay? So you don't have to have an electron go all the way. Let's say it's a 10 centimeter long copper wire, okay? You don't really need to have one electron go all the way from left to the right. You don't need that. By creating this electric field, you're telling all of the free electrons in that conducting material almost at the same time, because changes in electric field propagate with the speed of light, right? Very fast. So almost instantly, you're telling all of the electrons, all of the free electrons, the charge carriers in that metal to move, all right? So it's a shift of these charges. That's what we call a current, all right? That's what a current is. Now, you may be thinking, okay, what if they move? I mean, they keep moving to the right, fine, and they will end up accumulating on one side, right? So imagine all the electrons moving to the right-hand side, and they end up here because they can't go anywhere else, like parallel plate capacitors, right? In the beginning, they fill up the surface of the capacitor, but then they realize there's no more room to go. Where are they going to go? They can't jump from one plate to another. Same thing here. This conductor has a physical end. So if that happens, they can't move anymore, no matter what you do, right? Electric field may still be present, but they can't move anywhere. So if the right-hand side is negatively charged, this leaves the other side positive, okay? Sometimes in some materials, the positive charges are charge carriers, okay? Not for a metal, but for some cases. There are some examples where you may have positive charges too. But anyways, If the negative charges move to the right, the other side will be positive, relatively positive. So now you may think, okay, I know that there will be an electric field from positive to negative, and that's to the right. But I already had a external electric field, which was to the left. So away, a field to the right, a field to the left, won't they cancel each other? Yes, that's what electrostatic equilibrium is all about, right? I mean, you get rid of the electric field and the electric field drops to zero inside the conductor. So that's not what we need. I mean, we want a steady current, all right? We want a steady current. So in practice, what you really want is to complete this like a cycle, all right? So we're gonna come to that later, but imagine, what if you had a ring-shaped conductor, okay? And you started with some electric field that run through the conductor like this, okay? Then you would have these electrons move, right? Just to give you an example how you could have a steady current, all right? So you gotta have something closed, like a loop. Now, of course, just a loop like this, why would you have electric field in the first place, right? I mean, you have to create the electric field. You have to push the electrons, just like, you know, when you're watering your garden, there's a pump that pushes the water, right? So usually realistically, what you have is a circuit. And in that circuit, you would have a battery, which would provide the charge flow, right? The charge flow. We're gonna come to that. But just to tell you that, you know, this is only a limited view right now. We're only focusing on one part of the conductor and try to understand what's going on there, okay? So let's try to quantify this. So we have electrons, free electrons. Let's try to come up with a number, n, okay? This is the number of charge carriers, in this case electrons, charge carriers. It's a density, charge carriers per volume or per unit volume. Okay, it's a number per volume. So let's imagine we have a cylindrical conductor like this. And that, I mean, it's a cylinder with equal area. It doesn't matter right now. So we're talking about charges that flow Q to the right. Okay, now these arrows now represent the drift velocity, okay? So I know that the actual movement of the electrons are these zigzags, but since I came up with this idea of a drift velocity, let's stick with that, Vd, right? This is the drift velocity of each charge carrier. Now, I want to find how many of these charge carriers are there in a given volume, okay? So my volume could be a smaller portion here, like, okay, this is the cross-section area. So I'm gonna take from here to, let's say, over here. Okay, like a cylindrical segment of that wire. And the length could be delta x. All right, so the volume I'm considering is this base, which is A times delta x. This will be the volume. So the number density, which is n, times this volume, that many charges, so n times A times delta x many charges will flow through that black cylinder in delta t, okay? This will be the number of charges that will flow through the volume, okay, the one in black, in delta T. All right, so that will be number of charges, and each charge is Q, let's say. Q is the charge. If you multiply the number of charges by Q, you get the total charge, Q, okay, or delta Q. That corresponds to delta X, right? So delta Q will be this number, which is NA delta X times Q. All right, and delta X, as we found it over there, delta X is the drift velocity times delta T. So we have N times A times VD delta T Q. All right, so in delta T time, in delta T seconds, delta Q is the charge that flows through that area. So current is nothing but charge flow, okay? Charge flow per time. That's the definition of current. So current is defined as, and the letter we use is I. The letter we use to show current is I, is delta Q over delta T. Or if you think about an infinitesimally small time increment, we're talking about derivatives, or dq by dt. Especially if the electric field is changing, let's say, then V will change, right? Therefore, you will have a change in current. So this will be the instantaneous rate of change. So let's take a look at this now. We have delta Q here and delta T over there, so we can directly find I. Delta Q over delta T will be N times A, the cross-sectional area, times the drift velocity, times Q. Okay, so for a metal, since we're talking about electrons as charge carriers, metals like copper or aluminum, you know, we're talking about the charge, which is equal to, in magnitude, 1.6 times 10 to the negative 19 coulombs. Of course, electron has a negative charge. I'm talking about the absolute value, all right, of this charge here. And N can be found from a table, okay? So the number of free electrons, or the density of free electrons, density of charge carriers, will vary from element to element. So that can be also determined from a table. Basically, and A depends on the material you have, okay? I mean, every cable will have a different cross-sectional area. So that gives you the current, okay? So current is pretty much charge over time. Charge is measured in coulombs, and time is measured in seconds. So we're talking about coulombs per seconds. Instead of saying 1 coulombs per second, you say 1 amp. A stands for amps or ampere. All right. Actually, amps is the fundamental unit. Coulombs is 1 coulomb is 1 amp second is a derived unit, if you think the other way around. But basically, this is what we call current, all right? Now, although current has a direction, you don't really think of current as a velocity. It's just along the wire, okay? You change the direction of the wire, the direction of the current will change. Although we started with the drift velocity, and velocity is a vector, we don't really think of current as a vector. We'll have the current density though. So what is current density? So what if you take this current and divide by A? Then you will get NVDQ. Okay, we call this current density. It's like an area density, right? So amps per square meters, if you will. And we're going to call it J. Okay, J stands for current density, will be equal to NVDQ. All right. So this is actually going to be a vector, J. Now, remember, we started with electric fields. All right. Electric fields, and in this case the electrons were charge carriers. What if it was a positive particle? How different the current would be defined? You don't really need to change the definition, but I'm going to show you something about the direction, how to find the direction of the current. Suppose the electric field is to the left, then your electrons, which are negatively charged particles, well, they will move to the right because the force is to the right. Okay, so the electrons move to the right while the electric field is to the left. Okay, so I'm going to call this a right current. Or let's wait for a second. What if I had now positive charges? Let's say in my container here, I have some ions, all right? And these are positively charged particles. And I know that they're moving to the right. Let's say the velocity is to the right. This is the drift velocity. The electrons were also moving to the right. Okay, now I'm thinking if the protons, not protons, I'm sorry, the positive charges, if they are moving to the right, and that's the direction of the force, so the electric field should also be to the right. Okay, I'm going to deduce that the electric field actually was to the right for this case. Okay, so I'm going to call the direction of the current also to the right in this case. I to the right. Now, this differs from the first case because the electric field was to the left. Okay, now what if I have an electric field to the right? What if I don't change the direction of the electric field? It's still to the right, as in this case. But instead of positive charges, I have negatively charged carriers, electrons, in other words. Okay, now the electrons will move to the left. Okay, which in fact, what really happens inside a conductor, it's the electrons that move. But based on the electric field, it's still pointing to the right. So why don't I consider why don't I focus in the direction of the electric field instead of what the charges are doing, okay? Yes, if the electrons are present, they're going to move to the left. If the charge carriers are positive particles, they're going to move to the right. But in both cases, the electric field will be to the left. So I'm going to call, in this case, the current is also to the right. Okay, so this was my convention. Convention is the direction of the positive charges will be the direction of the current. I don't have to, if I just make that convention, I know that whether I have positive charges or negative charges, I will have the electric field pointing in that direction. Okay, so that's historically also correct. So the current is defined as the direction of the positive charges when they move. All right, so now maybe it's time to relate this electric field to this current density. All right, so here's the idea. If the electric field, first of all, we know that if the electric field is increasing, this is going to affect the charge carriers. They're going to move under the electric field. So that's going to affect the charge, the current density. So these two actually are proportional to each other, okay? And that's pretty much true for all metals. There's a linear relationship between the electric field and the current density. All right, so you may compare this to something you learned in Physics 1, Newton's second law, F equals ma, right? A linear relationship between the acceleration and force. And then mass here, m, is a measure of how difficult it is to change the velocity of an object, okay? How difficult it is to change the velocity of the object, whether speed up or slow down or change direction, doesn't matter. So if we have such a relationship between the electric field and the current density, don't we need a constant which would tell us how easy or how difficult, for that matter, it is to move those charges when an electric field is present, all right? So can we come up with a relationship like that? So E equals, let's say, a constant times the current density. So if this constant is large for a given electric field, you will have smaller current. And if this constant is small for a given electric field, your current density will be greater, right? So if that number is large, you have small current. So it is a measure of resistance, okay? You're resisting the motion of the electrons. Now, why would you have that resistance? Well, it depends on many things, okay? It depends from metal to metal, of course, from material to material. It depends on things like temperature, because although those ions have fixed places in a metal, they're in a constant vibration because of their atomic nature, all right? And that vibration means energy. So if you give energy to the system by heating it up, heat that metal, they're gonna shake more violently, okay? And when the electrons are trying to pass through those vibrating ions, they will have a difficult time, right? Imagine you walk in the hallway and there are students just sitting right and left, okay? You're trying to find your way between them. And all of a sudden they start jumping up and down or moving, shaking like this. It's gonna be harder for you to find your way, right? Same idea. So this resistance to the current should be dependent on the temperature of the metal. Greater the temperature, greater the resistance. So let's give it a name here. Let's call this rho, okay? This constant here, let's call it rho, the Greek letter rho, stands for resistivity. Resistivity, okay? This is also called Ohm's law, named after the scientist who discovered this, Ohm's law. Ohm's law relates the electric field to the current density, just like Newton's second law would relate the force, the net force, Newton's second, to acceleration. Okay. Rho is resistivity. And the reciprocal of rho, 1 over rho, will be called a sigma, and this will be called the conductivity. Conductivity. So copper, gold, these are good conductors. All right. So the dependence on temperature, okay, let's try to plot it for regular metal like copper. So let's plot rho as a function of temperature. And we're going to use, the Celsius, degrees and centigrade. So within, let's say, 100 degrees or so, we expect this dependence on temperature be something like this. Okay, so I'm increasing. But approximately, we could write it as, so rho as a function of temperature can be written in this manner: rho 0 times 1 plus some constant, some metal specific constant alpha, all right, times T minus T0, where T0 is some reference, okay? So, and rho 0 corresponds, rho 0 is the value corresponding to that resistivity at T equals T0. So when T is equal to T0 here, when T is equal to T0, rho is equal to rho 0. So maybe I should write rho 0 here. Okay, so this will be a linear relationship here. It's an approximation, but the slope will be equal to that constant here, alpha. Okay, so basically, greater the temperature, greater the resistivity. That's for regular metals. For semiconductors that you would find in microchips or transistors, semiconductors, it's the other way around. It decays. And there are also superconductors. When you go below a certain temperature, resistivity becomes 0. Okay, so you would have a semiconductor, or you would have a superconductor. It would be 0 here, below some critical temperature. All right, so that's the temperature dependence of the resistivity in a nutshell, okay? Now, this conductivity is the reciprocal of resistivity, all right? And E is equal to rho J, therefore, J, current density, will be equal to sigma, conductivity times the electric field. All right. And when you write the relationship in this form or that form, this is the basis of Ohm's law. All right, Ohm's law. Now let's apply this idea of resistivity for a really simple wire in the shape of a cylinder. Okay, a cylinder, a given cylindrical copper wire that you can buy from the store, right? Which has a certain diameter, therefore a certain cross-sectional area, and then you have a certain length. Okay, 12 feet long wire, let's say. And you want to use this wire in your circuit, and you want to know how much resistance it will have for a given current, right? Okay, so let's think this not in terms of E, but the potential difference between the ends. Because if there's an electric field here, remember, that's because, or that also means, let's say, there will be a potential difference between the left and right-hand sides of this conductor. Let's call these point A and B. So left-hand side is greater in potential. VA is greater than VB. And the difference, which we can call delta VAB, is equal to VA minus VB. So let's think in terms of delta VAB instead of the electric field itself. Like if I multiply the electric field, now this is a uniform electric field, okay? So integrating the electric field along that path simply means multiplying by the length. So E times L is delta V. All right, so my equation here, Ohm's law, said that the electric field was equal to rho times resistivity times current density. So electric field is equal to rho times current density. So in this case, if the current that flows through this wire is I, I'm talking about this I divided by the area. So rho times I divided by area. But the electric field, based on this, is now equal to delta V. I'm going to drop this A and B. You know what I'm talking about, right? Delta V, potential difference, divided by L. Okay, so delta L over V is equal to rho times current divided by A. I'm going to solve this for rho. Okay, did I write it wrong way? E equals rho J. Double check again. Equals. Okay, so delta V will be equal to rho. I'm not going to solve for rho, I'm going to solve for delta V. Delta V will be equal to rho times I times A times L. So L divided by A times I. Now, rho, remember, has to do with the metal, okay? You can look it up in a table. But L and A, on the other hand, depends on the specific wire you're buying from the store, okay? You can buy a bigger gauge wire or a smaller wire that will change A, or you could get 12 feet or 24 feet. Okay? L, it's up to you. So these parameters here, L and A, may vary for a given rho, but basically we're multiplying constants, okay? These are all constants. What may change is the current. So the current changes based on the potential difference. It's a linear relationship. Greater the potential difference, greater the current, okay? A linear relationship. And this constant here, if that constant for a given potential difference is small, then the current will be high. to keep delta V the same. If that constant is high, the current will be low. So it's just like this resistivity, but we already use resistivity here, so we're going to call it resistance. Resistance, capital R. Okay, resistance for a metal is rho times L over A. And this is another form of Ohm's law, if you will. Maybe more famous than the one I already wrote. So delta V equals I times R. All right. That's also due to Ohm. And the unit for R will be ohms. Letter omega will be ohms. Okay. So that's the unit for R, resistance. What about the unit for rho? Now use this equation to determine the unit for rho, right? You have 1 ohm on the left-hand side, let's say. Now the unit of resistivity, rho, times L, that would be in meters. A, that would be meters squared, square meters. Therefore, the unit of resistivity, this cancels that, is ohms times meters. Okay, when you look up your number in a table, okay, copper resistivity, such and such, omega meters, ohm meters, I'm sorry. Okay, so that's the unit for resistivity. Of course, the unit for conductivity, unit of conductivity would be 1 over ohm meters. And just like we could write resistivity as a function of temperature, we can now write the resistance also as a function of temperature. Okay, can I call this alpha? I guess I can. Alpha minus T naught. All right. Now, what if the shape is not a cylinder, okay? What if the shape is not a cylinder? Remember, we ended up with this relationship here between the length of the wire and the resistance and the area. What if we have some irregular shape? Or before irregular, it's just like, what if it's a cone? Well, a cone is not an ideal shape because you don't want it to go to a 0 diameter here, then you would have any current at all. Let's truncate this over here. Something like that, like some changing area, basically. So this could be your X direction, Y, and the current you're trying to apply here is going this way. But the obviously the area in this formula was for a cylinder. Now that cross-sectional area is changing here. Okay, let's call this R1, radius 1, and this is radius 2. And then the height of the cone is h, let's say. So this is x equals 0, and this is x equals h, okay? So which area are you going to use? Is it pi r1 squared or pi r2 squared or average, okay? So we better work with differential arguments like we always do in this type of problems. So I'm going to take an arbitrary x here, arbitrary x. At that point, the radius will be y, okay, whatever the y value is at that point. So the area now becomes pi y squared, where y is a number between R2 and R1, okay? And what about the length? Am I going to take the whole length, h? No, I can't do that because I know area changes. It depends on what your x is. So I'm going to take a very small, an infinitesimally small. I'm going to exaggerate now a little bit and make it bigger than it really is, but it's a very small increment from left to right. Okay, the small increment is differential. I'm going to call it dx. So the assumption is if you move just a dx, the area doesn't change that much. And within that tiny cylinder, I could apply that formula, but I'm going to call it dr. Okay, this black area here, black section of black disk, that section of the cone, the truncated cone, will be equal to dr. Same rho, that's fine. There's no problem there, rho. But instead of L, I'm going to use dx. That's the dimension. That's the variable in that direction, dx. And area is pi y squared. Okay. So if I can find the contribution of each disk, one after another, and find the drs for those and add them up, that should give me the actual resistance of the cone. Okay, that's the idea. So I will need to integrate. The r that I need to find will be the integral of dr, in other words. Okay, I'm going to obviously integrate over x variable. That's fine, but there is y in the denominator, and y does depend on x. So y is a function of x. So let's find that function. Plug it in here and then integrate. Okay, so what is y in terms of x? It's actually, just concentrate on this part here. Let this be, let's say, on the z equals 0 plane or something, okay? The third dimension that I didn't draw here, that's the z direction. What if z is 0? We're talking about y, x plane, and on that plane, that black line is a straight line, and we know how to find the equation of a straight line, right? So you'll basically need an intercept here. That's when x is 0. That would be your r1 plus, it's like y equals mx plus b. B is your intercept. We took care of that. M is the slope, okay? So the slope of this line, it's a negative slope, all right? So we would have negative here, negative, and R1 minus R2 divided by H times X. Okay, let's try it. Let's see if it works. So when X is 0, Y is R1. Okay, that's fine. Y is equal to R1. What if X is H? And these cancel. R1 minus R1 is 0, and minus negative makes positive. When X is H, Y is R2. That also checks out, okay? So that's fine. Let's just plug that in Y here and integrate over X. Now, rho and pi are constants. I'm going to write them in front of the integral. Rho over pi, integral x equals, from x equals 0 to x equals h dx over y squared, which is r1 minus r1 minus r2 over h x. Squared. Or I can get rid of the negative sign here. Why don't I write it as, let's make some room here. Okay, so why don't I write it as rho over pi from from 0 to h dx over r1 plus r1 minus r2. I'm going to make it r2 minus r1 divided by h x squared. Okay, so from the integral, I will have h divided by r2 minus r1 times 1 over r1 plus r2 minus r1 over h times x, right? And did I forget a negative sign? Yes, I did. A negative here. Let's put the negative right there. From 0 to h. The answer will be positive, okay? R is positive. So if we get the wrong answer, we have to fix that negative, but let's see what we get. So negative rho over pi h r2 minus r1. Now, if you plug in h for x, then you will have r1 plus r2 minus r1, which is 1 over r2. Minus, if you plug in 0 for x, then you will have 1 over r1. Okay, so this will give me negative rho over pi h over r2 minus r1 times, okay, what do I have here? R1 minus R2 divided by R2 times R1. Okay, so denominator R2 minus R1, numerator R1 minus R2. So these two cancel to give me negative 1. That negative cancels the negative in the front. So this is equal to positive rho times h divided by pi divided by R2 and R1, okay? That is your resistance of that cone shaped or cut cone, truncated cone, whatever you want to call it. That shaped conductor will have a resistance like this. All right, it's still linearly proportional to h, which is as expected, okay? Longer the cable, greater the resistance. But in the denominator, it's not R1 squared, it's not R2 squared, it's pi R1 times R2. Okay, I mean, you can, you can have many examples. What if you had something like this? A prism-shaped conductor added to a cylinder. Okay, maybe your, let me try to draw this nice, okay? So you have prism, a square prism, let's say. So this is your conductor. The wire that you buy is this shape. And then you have another piece of wire, which is a regular cylindrical wire, like this. And you solder them together, let's say. And then you want to find the resistance of this wire, okay? So this is L1, this is L2, okay? So each conductor, each wire is uniform as long as you stay in that area, meaning the cross-sectional area here is the same as this area, okay? And then the cross-section over here will be equal to that, which means it doesn't change as you move to the right. You don't need any integration to do that, okay? You can just apply the formula directly. So all you need is an area. Let's call this A, and let's call this, I don't know, D, I guess, diameter. So the area will be A squared, right, for instance. So the resistance of the first wire, let's call it R1. R1 will be equal to rho, whatever material this is made of, These could be separate materials too. What if this is row 1, copper and aluminum, row 2? Now row 1 times L1 divided by A1, which is A squared. And then R2 here, on the other hand, will be row 2 times the length L2 divided by pi R squared. R is the half of D, right? So the resistance of the wire after you do the soldering would be R1 plus R2. That's what you do with resistors, okay? If you add them one after another, if you line them up, since with length resistance goes up, you can just simply add the resistances like this. We're going to talk about those in detail later, okay? So just an example of how you could calculate the resistance based on that simple formula, okay? You can either integrate it or just apply it. Right, this one here. All right. Now let's talk about the source for this current, okay? Yeah, we have a conductor, fine. We have electrons moving in the conductor, but why are they moving? Why do we have electric field? Remember, I talked about a water pump, right? So where's the pump for this? Now that's what we call EMF, electromotive force. EMF stands for electromotive force. It's not a really good name. It's not really force, okay? It's not a force. What it is actually a potential difference. So not really a force. It's just a name, okay? It's a historical name. It's not a force, but a potential difference. It's measured in volts. Difference measured in volts. Okay, so you have your conductor, cylinder, rectangle, whatever, but you need to supply that charge flow, and that will be done by this EMF, which could be simply a battery, right? Your car battery, 12-volt car battery, the positive and negative terminals. Yeah, that's what is going to do this job, okay? So you just connect this. Okay, first of all, never connect a wire, just a wire, directly to your battery. It's dangerous, okay? Because the resistance is very small. You have to have a load. You have to have a load. A load is a resistance. Something is better than a copper, right? Or you could have a really long copper, that would increase the resistance too, but never try this at home, okay? Never try to short the terminals of your battery. Just because I drew it here, don't do it, don't try it. It's dangerous. Why? You will have a huge current all of a sudden. It's gonna create sparks and then maybe melt something and maybe even start a fire, or it's gonna explode, who knows, okay? It's not good. You should always have a load here. The idea is to complete the circuit, okay? It's a circuit now. Complete it, but you should have a load. A load means a reasonable R. Reasonable R. Because remember Ohm's law is delta V equals I times R. So if you use a car battery, 12-volt car battery, and if you want a 1 amp, which is reasonable current, it's a lot of current, all right, then your resistance should be at least 12 ohms. All right. So, so what does this battery do? Okay. Now, think of this battery. This is your box, okay? This is the box. You should have a positive side and a negative side. But what you really want is the current to go like this, in that direction. Okay? Remember, if the current is going that way, which means electrons are actually going the other way. Electrons are moving to the left, which means electrons are moving from the positive terminal to the negative terminal inside the battery. But you know, that's not really what these electrons would do, right? Electrons would go from, would move to the positive side, right? They will be attracted. But that's where the chemical reactions, you know, are doing their thing, actually. They're pushing the electrons. Electromotive force is actually like a pump, pumping the electrons in a certain way. So that's the chemical process there that forces that, right? Just like in your water pump, it's the mechanical motion of the engine that does the job. Here, the battery does it. So we call that potential difference that is generated by the battery the EMF, and the symbol is E, the curly E. This stands for EMF. But we can't really say the potential difference between the terminals is EMF. Okay, in practice, that's what you want to call delta VAV. Remember the terminal voltage? So this terminal voltage actually will be less than the actual EMF. And that's because the battery will have some internal resistance itself. Internal resistance. And we can call that little r. Okay, so when that current goes through the battery, this EMF will be reduced by that amount, which is equal to I times R. And that will be equal to the potential difference across the terminals, delta V. All right, that's for a battery. Now, by the way, the symbol for a resistor is this zigzag line you will see in circuit, diagrams. That means resistance. So we have that R. And this battery, batteries are usually shown with this symbol here, or EMF, let's say. Okay, a long line, which stands for the positive, and a shorter one, which is the negative. So that's the EMF, which forces the current in this direction when the circuit is completed. But it has an internal resistance. So that's little r. So these two is actually what is a battery, okay? This is the battery here. Now, if you complete it to a circuit, this means you're now adding this load and then joining the other end to the load. Now you have a circuit, okay? So this current goes through the battery. It means schematically it's going through the little r, internal resistance as well. And then leaving the terminal here, remember the battery over here, this side, it's leaving and then entering your load. This is the current. And then going back to the negative terminal of the battery, okay? It goes like this. So for a current to exist, there should be a complete cycle, a loop. Otherwise, you won't have any current. Suppose you soldered a wire here, over there. Let's use red again, okay? But there's nothing connected to the other side. So the charges will move on this branch. They will never go into that branch, okay? That's just left by itself. There's nowhere to go. I mean, there's going to be no current here. No current on this part because this side is open. Maybe you're thinking, what if I take this and then connect it over here? All right. Now the thing is, this cable itself is actually has a resistance as well, right? I mean, this is pretty much the load. This could be your car's lights, all right? But the wire itself also has a resistance, okay, which I didn't really show it here. If you think like this, the current will split into two and then join again over here. So you're pretty much, by putting, you're just changing the cross-sectional area of the wire for that section, okay? So that may be the only effect, which will not really change the current that much because the wire has a very small resistance compared to the actual load, which is your light bulb, let's say. Okay. So that's just to show you that you have to have a circuit completed to have a current. Excuse me. So delta V, how does delta V or how does potential in general change? Okay, so let's pick some points here. Let's call this point A. Okay, and then there's nothing here. And then this is still point A in that manner. Okay, so this is still A. But now we cross over and we are here between the two R's. That's point B. That's the negative terminal of the battery. Okay, and then I can call this point here point C. See, there's not really a physical point C inside the battery. You understand what I'm saying, right? I mean, this little R represents what's happening between the two terminals anyways. But when I write it down in the form of a diagram, since I can separate the EMF and the little r and call that my battery, I can call that point C. Once I move to the diagram, I have my point C there, right? So let's plot the voltage now. See how it changes. Okay, it's a 12-volt battery, right? So I need to go from 0 to 12 volts, let's say. 0. See, delta V is a difference, okay? I mean, if you pick one side as 0, the other becomes 12. If you pick one as -6, the other one becomes +6, because the difference is 12, right? So the voltage is going to go from 0 to 12 volts. And here below the picture here, I'm going to draw a representation of the circuit here. So let's start with the EMF directly. So here's the EMF. Negative side on the left, positive on the right, I'm going to do. And then I'm going to put that R. So this R here, I'm going to copy it over here. So that's what happens. This is point A, remember? And I'm starting with point C. And I pass R, this is EMF. And now I'm at point B. And from point B, I now enter the battery. In my diagram, that's where I put little r, the internal resistance of the battery. Little r. Now I'm back at point C again, all right? C. If you want, just combine them like this. Same point. But what happens to the potential? Now, I call this 0, but once I go through to the positive terminal, I need to read 12 volts right there, right? So I start at 0, but when I reach here, my voltage becomes 12 volts already. Okay, so when my current enters the resistor here, the voltage is 12 volts at that point. But according to Ohm's law, remember, which said delta V equals I times R, I could apply this to R only and view this delta V as the potential drop across this resistor here. Okay, the potential will drop from VA to VB. Whatever that value is, depends on R. So, something like this. Actually, you know what? Let me just draw this line here for where R is. Like this. And I'm going to do the same thing for the EMF. Or I could just go on a straight line here. Straight line until I hit R, okay? But it's going to be a potential drop from A to B, like this. Okay, so the resistance of the wire is negligible, so it's a straight line. And then when it goes over the other R, the little r, it drops again. Okay, so how much do these drop? Here, this difference is equal to I times R. But here, this drop in the potential is equal to the same current, but now times little r, the internal resistance of the battery, right? So this means if I add the two, IR plus I little r, I get the actual terminal I'm sorry, not terminal. I get the actual EMF. All right, so EMF here. EMF. So the terminal voltage is VAB, right? So delta VAB is nothing but IR. And that's equal to E minus IR. Okay, so that's where that relationship between EMF and the terminal voltage comes from, the one that I wrote over here, okay? So that's the logic there. Okay, so that is the E is EMF and VAB is the terminal voltage. So it's pretty much true for all batteries you buy from the store. So what happens is you use your battery, for a while, and towards the end of its lifetime of the battery, this internal resistance R starts increasing. So when this goes up, this means your battery is almost dead. Okay, I mean, the battery will not run your maybe flashlight, but if you connect it to a voltmeter, it'll still show you some number, right? But it won't be enough to do the job there. That's what happens, when batteries get old. This means their internal resistances increase. When they're fresh, R is small, and then R gets bigger and bigger until you can't use the battery anymore, okay? After all, it's just some chemical reaction inside the battery, and it runs out of juice, okay? All right, so if it's a rechargeable battery, you just plug it in like your phone, right? It works the other way around. So the next thing I'm going to look at is look at this thing in terms of energy, all right? Energy concepts. And we can finish the chapter with that. So let's summarize what we did here. So we have resistors. Let's say R1. You may have a load which is made of two objects. And this is your, let's say, two light bulbs. Light bulb 1, light bulb 2. All right. Or any load. A resistor, the commercial resistor that you can buy from Radio Shack is something really small, okay? Looks like this. There are color codes here. You can look up the values of those numbers, of those colors, and you'll know how many ohms that resistor is within a certain tolerance, which is also a color there, right? So let's say you find two of these and connect them like this. If you remember the capacitors, how we connected them in series and parallel, we can do the same thing here as well. Suppose you had it like them, and then you have this internal resistance, and then you have your EMF. It's the positive terminal. So there will be a current going through the circuit, all right? So when this current, every time it goes through a resistor, the potential drops a little bit, okay? Now, let this be the terminal A and terminal B again. This is your battery, remember? Battery. So points A and B are the terminals of the battery, positive and negative terminals. So now call this point C. Now VA is definitely greater than VC, and that is also greater than VB. Okay, the potential drops as you move with the current. So when you move from left to right along that line, from A to C and from C to B, you're moving with the current. The current is also in the same direction. Okay, actually, I mean, current doesn't move, right? Current is moving charges that are moving. So I use it wrong, okay? It's current doesn't move. There's current there, which is charges moving. So if you're moving with the positive charges in that sense, potential drops, okay? And every time you go over a resistor, the potential drops by an amount equal to that resistance times the current. So VA minus VC, which is delta VAC, would be equal to I times R1. Similarly, delta VCB will be equal to what? I times R2. If you add these up, delta VAC plus VCB gives you delta VAB. From A to B, the potential drop is I times R1 plus I times R2. Okay, so B is the lowest. No, actually the lowest point will be between the EMF and internal resistance, but that's what we did before. Okay, so you can analyze the currents like this. So current is to the right. What if you are moving from right to left, going from B to C and then from C to A? Now you're facing the current, so the potential increases. Okay, it's like rowing your boat against the current. Right? Same idea if you're going uphill. Okay, current means from up, downhill, just like river would flow from high to low, right? So the last thing I want to talk about today is, I said energy, right? Let's think of these in terms of energy concepts. Like, let's start with, if you move a charge through a potential difference V, that's energy, right? That is energy. And when you get your electricity bill from the power company, you pay for the energy you used, right? But on the other hand, it's good to know if you know what happens when you, let's say, you use an electric bulb versus iron versus, your computer. I mean, these use electricity not the same way, right? Some are more expensive to use. When you charge your phone, you don't really worry about that much, but when you're cooking something, when you're boiling water, you know that you're using more electricity. You should, right? So we really think in terms of energy per time, which is power, right? So we divide this by time, divided by T, or better say delta Q, delta T, right? That's the idea. So this will take us to power, energy per time. So since current is defined as charge flow in a given time, if you just multiply it by, see there's the current here, you multiply it by delta V. This gives you power. This is measured in watts. Okay, 100-watt light bulb. Now, so if you know that your delta V that you use at home is 110 volts, Now, this is actually called an AC current, and we're only doing direct currents. We're going to go there, so let's not worry about. Let's just use. How about a flashlight? Okay, a flashlight maybe uses 2 batteries. That would be 3 volts. Okay, those batteries, AAA size, it's 1.5 volts, and you could use 2 batteries like this. One battery connected to another battery in series. And then this is 3 volts, because 1.5 is each, right? So delta V is 3 volts. And then, okay, you want to get how many watts? Let's say 20 watts. If you have 20 watts, what will be your current then? How much current in amps or milliamps for 3 volts? That's how you can find your current, okay? So 20 divided 3 by 3 amps. It's a lot of current, actually. Okay, so a flashlight will hardly give you 20 watts. That's a lot, right? So power is I times delta V then. So how do you interpret this? This is the energy dissipated in a resistor, right? This is the energy dissipated in a resistor. What happens when you force a current through a resistor? You heat it up, okay? So this dissipation may happen in the form of heat, pretty much. So you can write it different ways, of course, using Ohm's law. So V equals IR, so it's also equal to I squared R. Since V is equal to IR, delta V is equal to R, according to Ohm's law, I times I squared R. Or you could get rid of I, which is V over R, so you would have delta V squared over R, okay? 3 ways of writing power. Your electricity bill doesn't say anything about power. It's about the energy you use. So how do you go to energy from power? You multiply it by time, okay? So the unit will be watts times, what's the time for unit? Seconds. Well, you don't have that, your energy bill, you have hours. So kilowatt hours, this will be the unit. Okay, 1 kilowatt hour is 20 cents, for instance. Okay, that's the energy. You can use that energy in 1 day or in 1 month. They don't care. You only pay on the energy, not the power, based on the power. Okay, so these are the formulas for power. And through a resistor, that's how we interpret it. The energy dissipated through a resistor. Now, remember, delta V for a battery terminal voltage is EMF minus IR. So if you multiply it by R, then you would have EI minus I squared R. This will be the power from your battery, okay? So this will be this is what's going on in your battery. If you're charging your battery, okay, read this in the book, you would have a positive sign here. EI plus I squared R. This will be the energy you would need, power, I mean, when you're charging your battery. But when your battery is discharging, this is the power. And then when that current is running through a resistor, this is the I squared R is the power, energy dissipated, the rate of energy dissipation through that resistor. Okay, so the last thing I want to talk about is actually, let's go back to the beginning. Do you remember when I mentioned what happens to these electrons in the beginning over here? Okay, so let's try to analyze this motion better. Let's use classical physics. Classical means apply F equals ma. So this picture is actually like this. Let's say without the electric field, the electron would move some arbitrary like this, okay? So the average, on the average, they don't move anywhere. It's like a random walk. But when you apply an electric field, they will end up moving. So when they do that, this is what I showed with red before. It's actually more like this, a curve. Oops. It's more like a curve. Okay, and that's because of this accelerated motion here. Now this V is equal to A times T, right, from kinematics. Now let's use this idea here, F equals ma. So F is Q times electric field, right? So we have the Q times electric field equal to mass times A is V over T. V over T. Now, let's recall, okay, let's use one of these here. Let's use J. Let's use the relationship between current density and electric field. We could use the one with resistivity, or we could use the one with conductivity. So J equals conductivity times electric field. And J is current density. Current density over some A, right? So why don't I just use, let's say, I think I found the formula. Yeah, let's use this here. Let's use this. So instead of J, I'm going to write N drift velocity NBD Q. Okay, that's equal to sigma times E. And I'm going to replace E with M V over QT. Okay, so I take this now. There's Q, it makes Q squared. Q squared times V. Okay, I guess the V's cancel, huh? Do I really want to cancel V? Well, if I cancel it, I get Q squared divided by M times N T. I think in the book you will see the letter tau for T. Doesn't matter. Let's keep it as T. This is the average time between collisions in an electron and in the conductor. So this T comes here. That will be equal to sigma. Okay, if I solve it. So some kinetic theory for conductivity, if you will. Let's compare this to the formula in the book. Let's see how they did it. I think they did it in conductivity. So, they did it in terms of resistivity, which is 1 over sigma. It doesn't matter. N Q squared over M times T. All right. So you could write it in terms of resistivity if you wish. That would be rho equals m divided by n q squared t. Okay, they just use tau for time, and q is the electron charge. 1.6 times 10 to the negative 19 coulombs. Okay, so that finishes this chapter. The next chapter, we're going to talk about actual circuits. Okay, DC circuits. And it'll involve resistors and also capacitors. Okay, and then we can move on to magnetic fields after that. So I'm going to stop this video here. Let me zoom out here and see if there's anything I didn't mention. Well, pretty much talked about many things here. Okay, that's good. So I'm going to stop here, okay? So until next time, goodbye.